and you can do over and over. So before, the prediction of the words was dependent on the previous words and of all of these words. Now we'll make it in such a way where you have it not using the same encoding of the words always, but we're going to use a new encoding of the word at every time step. And so we have what some people call it an attention module. I personally like the term attention gate, because the same idea of as a gating, like deciding which information. You have all these words from the source language, and they could all be encoded in the same Z, but here I'm going to decide that only a subset of them at any point in time. And dynamically, I'm going to decide these weights, these attention weight. Often people use the letter alpha. I will use this attention weight, and this is just a weighted average. And that's what will define my attended information, what you could call a context into that. And so these attention weights are, in fact, just scalar from 0 to 1 on how important. And you will usually do it in such a way that they sum to 1. That's often the case, so that it forces it to focus. It can always decide to maybe have a complete flat, but usually because of the way you optimize, you would put some constraints to also make it more peaky if possible. So how do we determine the alpha? We want them to be normalized, so we'll often use a softmax. And so then these are kind of the by default, these are the output of how important each words is. And these could be like as input as any softmax. These could be from plus infinity to minus infinity. They're the output of a neuron. So depending on the kind of activation function, they could be minus infinity, plus infinity. Maybe you don't necessarily want them that far. So often the activation function itself will either be 0 to 1 or minus 1 to 1, but often just 0 to 1. And so then this is becoming just a normalization, the softmax from this. And so the core, the gate, what will the gate do is the gate will be looking at the previous seed that you had, so the previous one, and then the latest seed, and then just find the projection to this for each. So S here, the notation just to make S is sorry, I said seed, but what I meant is not it's the sample, S for sample. And so in the case here, so every S could be here. I use so the hidden state as input to this in this case. So here's is the seed, and the H are each of the words that you have in your sentence. So the seed will change. So that's why the alpha word had two indices. This is for the seeds because the weights are going to be different. The first seed, the second seed, the third seed. And these, in the case of the machine translation, was at every time I generated a different word, I got a different seed. And then I will see for every word, and that way I will get a different attention weight. Okay, and so basically we're running using a neural network to tell us where neural networks should be looking. So it's kind of interesting. So we have the encoder, it's a neural network. We have the decoder, it's a neural network. But then we have this other neural network, which you could almost see as a multi-layer perceptron or something. That's this gate that is going to tell me where should I focus my attention? And so now, how should I do it? I could do with a simple, like I said, I put it here, a multi-layer perceptron, but you could make it as complex as you want. And which input you can put there, there's a lot of variations on this. Maybe you could use all the seeds, only the current seed. Maybe you could use on all the words at the same time, and instead of just one word. So if you want to do on all the words at the same time, maybe you will make this as an RNN instead. So we can use RNN, GRU, LSTM. We can make it a bidirectional, so the attention could be bidirectional. All of the above. So the main key here is, as long as it is differential, as long as you can get the gradient, and then you can do backpropagation. And so once you train your model at test time, you get your sentence, you go and you, with the first seed, will find, like the start token, for example, find which word are the most important for that first seed. You will use it to make your first prediction, and you go over and over. You can plot this, and that's why many people got excited also with attention, because they were like, oh, this is definitely an improvement for interpretability, because suddenly I can get and see for generation of D, what was the word, the token that was the most related or useful for it. And what's really nice is French and English will have often a different ordering with adjective and nouns. So, so the greenhouse will be in French, will be the house green. And so there will be, and you can see it very clearly in this case. So zone economic European will be European Economic Area. So very different, and you can see it also nicely coming out there. And on top of it, the most important is that it improves classification. And so how it gives a soft alignment between sentences. It's done in an iterative way, and that's where the other self-attention that we will talk next Thursday will allow you to do it all at the same time, aligning all of the component at the same time. But right now we did, although we look at all words for the French, for the English, we were only doing one at the time. The module, the attention module, was called one at the time. But how do you do it multimodal? The word to word, that was great. We kind of, words were very nicely segmented. They are like tokens by default, so you can decide where to focus. But what if you have an image of like 1,000 of pixels by 1,000 of pixels? How can I use attention and do it in a multimodal way? And very quickly, when the machine translation attention model came out, very quickly there was this nice landmark paper on show, attend, and tell. And there, what was nice is that they were showing for image captioning, as you do the captioning of a woman is throwing a frisbee in a park. The idea here is that every time I generate a word, to see which part of the image will be the word most helpful. And now, so some words, I will say it's very ambiguous, and it's like, where would it ever like look at this part of the image? Very ambiguous. But in the case of like some entities, woman, you could say both are the gender female. Definitely there's a girl and a woman, but let's say that the algorithms still see both of them is ambiguous. But then throwing clearly is focusing more on the frisbee. Now, if definitely the word frisbee is even more focused, and the park is looking around. And so this is nice. And now you can see a little bit the challenge of interpreting these attention module, as you can imagine. But how can we do this with current representation? So most of the visual representation will use CNN representation, not canonical, but correlation, convolution. Sorry, I had too many C's recently. Convolution neural network. And so the goal will be to take advantage of these representation. But if you want to do the typical CNN for CNN for image captioning, so we'll take the CNN, get a feature, and then from that feature use it as a seed for the RNN as a way to generate. But if we use the latest, like if you remember, the CNN takes the image, you have convolutions, you have pooling, convolution, and then at the closer to the end, we'll have a few fully connected, and then we'll have your vector often of size 3000. So one question is, can I use that vector of 3000? But the challenge there is then that vector of 3000 doesn't have any more link with the image and the spatial aspect of the image, because the first dimension of that 3000 doesn't mean it's any way related to the first pixel. So it's tempting to use the last one, but it will not give us nice spatial information. So instead, what we'll do is roll back 2 layers before that and look at the last layer that is a response map to the convolution. And that one, if you remember, if you have, let's say, 16 by 16, or let's say even simpler, 4 by 4, they are the response of convolution kernels, which are like patterns or convolution kernels, related to one part of the image. If it's 4 by 4, then it will be closer to the top left corner. And so now you have values that are not only informative about what is visually in there, what's visually, which, and if you remember, you'll have maybe 4 by 4, but you will also have a third dimension, which is all of these convolution kernels. And so now you have a kind of, for each of these 4 by 4, let's say 16 locations, you have a vector of, let's say you have 50 kernels for the last layers. So you have a vector of 50 times 16, so like 4 by 4, so you have a vector. And so now what you can do is take a seed, let's say the token start, and then learn some attention weight that will say, from all these 4 by 4, which of them are the most important given my initial seed. And then it will look at these 4 by 4 and give a weight. And so how many weight do you have? If it's 4 by 4, 16. You have 16 weights. And this will be, these weights will be one weight for the whole vector of 50. So you will have a weighted average, which will be a vector of 50 times its weight, attention weight, another vector of 50 times its attention weight, another vector of 50. Something that's a little bit confusing is you don't get an attention for every kernels. You get an attention on one vector, one value, one scalar for the whole vector of 50, but you have 16 of them because you have every location in the image. And then you get, so Z1, what will be the dimension of Z1? 50, 1 by 50, okay? And then I can use that to predict my first word, and I will also use that seed to predict my new attention, and then I can use this attention to predict the next Z, and then I use that to predict the next words, and then continue like this. And so what's really nice here is that suddenly I found a way to take an image and attend to part of the image. Now, what are the issues with this? What do you think this is the perfect way of 4 by 4? Like this, is it the perfect way to attend to an image? like take an image like right now that of me, and like, is it really the right way? And maybe I'm lucky because the face is within one, but maybe my face will be cut in half, and then, so half of my face in one bin and half of the face. Now, as you know, the convolution kernel are kind of overlapping, so so they're not exactly cutting it that way, but still the objects may be in one of and not the other. So for that reason, there's also other ways to look at it, which is more of an object base, where you will first maybe do object detection and characterization of it, like RCNN, and then you could do attention on top of that, which objects are useful for the prediction. But in general, self-attention allows for latent data alignment, so that's an implicit. It allows to get the idea of what network sees and can optimize using backpropagation. And also, it was really interesting to see all the extension. There was the initial paper about show and tell, which was just about image captioning, and then a lot of other papers after that, which was extension of attend on this. So really entertaining papers name. So this is self-attention. That's one of the three that I want to discuss. I want to talk about spatial, which is, I will say, the most relevant for images, but I want to put this seed in your mind, and maybe you think of a way to make it multimodal. So I said one of the challenge is that in the typical attention is that I will take a grid, because I use the last layer of CNN, or the last convolution response layer of CNN, and then I will select a subset of these small regions, but really maybe the object is only in a sub part of it, and so really it will end up in more than one of these elements of the grid. And so for one, I could do it an object-based approach, but another way to look at it is say, let's really focus on a subset. And so let me find a spatial transformation, and that comes from the computer vision world. Spatial transformation will be, can I warp the image in such a way? And in fact, you could call it, how can I crop? I think that's probably the term that people every day will relate to that. In computer vision, I will say maybe a warping function, but just here, how can I crop the image? So I have the original image, and I want to crop it in such a way that I can do my task, which let's say is object detection, let's say if it's purely vision, or it could be image captioning. I want to do the captioning, and so as a first step, I'm going to focus on a subset of the image, and then start my captioning, and then focus on another subset. And so for cropping, when you crop, there's 4 parameters that are typical, which is just a box around the object, and so it becomes the offset and the width and the height of it. And then you have your image of the crop image. And so can we make, the problem with cropping is like, it's by default is a very discrete thing. Is like 1 minute you're like with the whole image, and just the second moment you're with a very small bit. So it's a very a non-convex by default maybe. So what we will do is to make it a smooth process, is like instead of a very sharp process, is that you will find that function that learns this these parameters. You will learn a mapping function, like from an image, find a way to predict those parameters, and this is what we will call the spatial transfer network. And for this, I need to introduce a concept, and and this is the transformation, and there's different kind of transformation. There's the perspective transformation, and that's what makes it so that my hand looks bigger and looks smaller here. That's called perspective projection. There is also what is displayed here is affine transformation. There's other transformation where I could rotate my screen. So that's a rotation. That's a rigid transformation. And so, so the idea here is I can take points from any points in my image here, and I can apply a transformation and get the location of that equivalent point in this image. So instead of looking at it as a cropping, now I'm going to look at it as a warping, where you have a warping function that says, give me any points here, any point in the image, and I will find you, multiply by this matrix, which are going to become our new parameters, and I will give you a location in the target after the warping. And the idea here is that these will become parameters that I'm predicting. And so I'm going to have a gate that is going to take the input image and not do the warping, because I don't know how to do the warping yet, but I'm going to take an image, and that image as an input go to some kind of attention or like gate to create these parameters, and these will be used to create the image. And then I can use this and just confirm that the attention was correct, or maybe I will need to warp again and over and over and over. And then you can repeat this over and over. So this is visually what it looks like, is like you take original image, and then you will take that image, run it through some neural network, give you those parameters that tells you, hey, this is how you should warp your image, and then you get the warp image into this. And so you can see that this next network can nicely be optimized, and you can nicely do the gradient back propagation. And so now I can learn, give me any image, I can learn how to warp it to be as efficient as possible for my task. And my task could be for generation of language, or for, in this case, object detection. And this doesn't need to be complex in practice. And the sampler is this function, which is the warping function that warps this. This is a little bit, in the sense, warping in the same dynamic time warping. We were warping each sequence to be, but we were warping both sequence together in the dynamic time warping. Here we're warping only one sequence, but it's not a sequence, it's a 2D image, just so that you make a link with earlier in the lecture. And so you get an input image, and then you get the warping, which is the output, and then you get the, so even though the image originally is very warp, or you could say more warp, and then here you get, hopefully, and this is a lot clearer when the object is rotated, and then at that point you can do a nice rigid transformation to take that rotated object and bring it back. So this example, here they're plotting, and the points are just the corners of that bounding box. And so you can see how this is nicely bounding. So this is differentiable, and it allows you to do backprop end-to-end, but there's different kind of ways you can do the transformation. So I talk about affine transformation, there's perspective, you could do a spline version of that as well. So this is the second type. So it's no more like attention and gate to weight my sample, but it's an attention and gate to find that the output of the attention gate is not directly the weights of how important it is, but it's mostly a parameters for a warping function that will allow me to focus. And then the third one is attention. And I'm going to talk about one specific type of attention. We can discuss maybe more attention-based when we discuss reinforcement learning in week 9. But here, the hard attention is an example here is a glimpse. So the soft attention requires computing a representation for the whole image. The hard attention says only a subset is going to be the main, is going to be my focus. And hopefully, although it's debatable, is to also reduce computation. And you could say it's a little bit closer to how maybe the human does, although it is also a little bit smooth, the human. But the second keeps moving around, and that's the intuition that you get a little bit from it. So that if you're detecting a digit, the idea here is that you will look at pieces. And so if you're looking for the word, the 6, you may be looking a little bit more in this region, but still looking around just to be sure that it's not a 9 or it's not a 7 or another. So you'll start maybe somewhere, and then you will look around just to be sure that it is the digit you want. Now, they, in that exact paper, they made a decision, which I would say is not a requirement for this hard attention, but just so that you, which is the idea of having the very sharp field, like a very sharp attention with high definition, and then with having lower resolution and lower resolution. So the same image is in fact, for the same glimpse, you get 3 versions of it. This is really what I would call hard attention, but you, in their papers, they also include both. The others a little bit broader. And you can see that this will help you, because if you only see this, it may be hard where to look next, while this can give you information on where to look next. So once you given an input image and maybe an initial location, giving a location, then you can get these representation, and that gives you a response to like where to focus, and then you can merge that with just maybe just the location itself, and take that location and embed the location. So you kind of have a position embedding, which we'll talk about in the transformer. You could imagine, although it's done differently. And here you have a more appearance embedding, and then we'll merge both of them. So you could see it as it encodes what, like is at that position, and where. That's kind of what this is encoding. But the problem is how to optimize this. So it's differentiable with the location, with the glimpse parameters, but not the location, because it keeps moving around. And so to help with this, we'll go and look at something that's a little bit close to reinforcement learning. And so in this case, you have your location and you have your image. You will learn to this part is the same module I was talking about earlier, which is embedding the image. And then from there, you will predict an action. An action will be move left, move right, move up, move down kind of action. Once you get that, you get a new location. And then from the new location, you go ahead and you embed the glimpse. And then from that glimpse, you're going to get the next attention. And this, at the end, you can be sure there's consistency over time by having it as an RNN. That's what the RNN here is. So you can see the similarity with our reinforcement learning. For people who know already about it, we'll discuss it. And the emission network, this part is as an RNN. And the backprop is doable, but it is a little bit more tricky in this case. So today, and this is my last slide, we talk about explicit alignment, the idea to align 2 or more modality. And here in this case, the loss itself is the task itself, the loss itself, is alignment, dynamic time warping, extension to canonical time warping, and deep canonical time warping. The implicit alignment, which is the most popular one, will be, it's not the loss, but looking at different attention model. And so soft attention, hard attention, and also a different view on where the attention is giving you the parameters of another model, which is in this case was a transformer model. Okay, thank you very much for your attention.